So we're looking at elastic potential energy, and then we'll look at simple harmonic motion. A spring, I'm imagining, is something most people are familiar with. This is kind of a simplified version. I just took off a picture in the textbook, right? You've got a mass on a spring. So here it's just sitting there, right? And let's say you stretch that some amount. So you can see in the second picture here, you've actually pulled it. You can see where the force here is in the, you could call it the positive direction if you wanted to. Or you apply a force there, the spring moves some amount, let's call it X or delta X. And in what direction is the force that the spring exerts on the mass, right? Well, that's in the opposite direction here. Right? Similarly, if you compress the spring, right, you push in this direction, then the spring is going to push against you. So once again, it's going to push in the opposite direction. So now X would be negative, right? You've pushed it in the negative direction. And now the force of the spring would be positive. It would, again, be in the opposite direction. So just to go through those. And as a note here, I just wrote down that the spring force is a reaction or, restoring force. It's always acting to restore it to its equilibrium position. So whatever direction you displace it or it happens to be displaced at that time, right? If you let it go back and forth or whatever, that's always going to be a restoring force. That brings us to Hooke's law, which is a little bit, it's actually a really good, very helpful law. And it supposes, though, you're not displacing it so much that you're actually deforming the spring or anything of that nature, right? And a lot of things actually work that way. Steel beams and all kinds of things, we tend to use this law. It's quite helpful as long as you don't, again, deform it or stretch it or compress it too much so that you actually do permanent damage to whatever structure it is. And generally, this works pretty good, right? And really, just as it's written here, right, the displacement of the spring is directly proportional to the applied force and consequently to the force of the spring. So there it is written down as kind of a law. So the whole idea here is, if you look at the graph, it's saying, let's suppose you displace this some amount, right, delta X. So you displace it in the positive direction, right? This here might represent like 1 meter or something like that, right? Well, then you can see what would be the force of the spring would be, now it's not necessarily 1-to-1, right? Maybe the force of the spring here might be, 2 newtons or something, right? So it's not, I'm not saying 1 equals 1, but it's a linear relationship, right? If you then increase that displacement, you are going to proportionately, you're going to increase the amount of force. Okay? And if you, as we saw just up above, if you compress this thing, so that is if delta X is actually negative, then the restoring force would be in the positive direction. So that's why the graph looks like this and has this negative slope. And that slope is actually important, right? If you look at the slope of this, which as you know is just, delta Y over delta X, right? Slope is change in rise over run. So the y-axis here would be the spring force, so delta F of the spring, and that would be divided by delta X. And whatever this is, right, whatever this slope happens to be, if we actually test this and we say, okay, when we apply this much force, this is the displacement, we double the force, it's double, whatever that relationship is, we can work that out and we call that, we'll just call that K, and this K here is our spring force, or constant. And just like when we looked at gravity or stuff like that, we had, so it's just a constant that we put in here. And note that that constant is going to be different depending on the spring, sorry. What could be a string that you're using, I suppose? All right, so an example here, a weight is attached to the bottom of a spring with a spring constant, 45 newtons per meter. The other end of the spring is attached to the ceiling. When this is done, the spring stretches down by 15 centimeters. Determine the mass of the weight. Okay, so just trying to sketch this out, right? It looks something like this. Now we know that this thing is the mass is attached. It's been displaced, right, because of gravity. So before we attach this mass to this spring, we could assume there's some, let's call this like its equilibrium position or whatever. This is where it would be. And now I'll just use the center of mass of this. Now it's this, right? So this will be our delta x, which we're told is 0.15 meters. And from that, and I might even also just note right on my diagram, K equals 45 newtons per meter. Consistent with the slope of that graph we saw there, right? So if we look at the mass, we could even do a free body diagram if you want of the mass. And we can look at what are the forces on this thing. We can say, well, we have, at this point, it's balanced, right? At this point, the mass is just sitting there, right? It displaces the spring, but now it's not moving. So now the forces are balanced, and we know the two forces on it are gravity and the force of this spring, which I'll just put as Fs. So we know the sum of the forces in the y direction must equal 0. I've defined up as positive, so that means Fs minus Fg must equal 0. And the spring force, right, is just minus K delta X minus Mg. Putting in the numbers here, K is 45 and delta X is 0.15 minus the mass, which we don't know, times 9.8. I would move that to the other side and then just say M equals negative. Oh, sorry, I missed the negative here. I always hate it when I know I'm about to get a negative. Yeah, we said that we said the y direction is positive here, so that means this displacement over here, this delta x, is actually negative itself. So in my haste, I didn't write that as negative. Negative 0.15. So that way when I multiply these two things together, they should cancel out. And so that will give me 6.75 when I multiply those two numbers together. And then I divide both sides by 9.8. And that tells me that the mass of this thing is 0.689 kilograms. Once again, just to revisit that, that is our equation for force, right? It's negative K delta X because the force that the spring force that you have is always the negative of whatever it is, right? Because if delta X is positive, the spring force is negative, right? If delta X is negative, it's positive. So it's a reaction force. So it just goes back to that. Because yeah, it feels a bit weird sometimes when you're putting that in there, but that, and you can see it actually does work out, provided you remember to actually put in a negative delta X when it actually is, in the negative direction. All right, since we're in the energy unit here, right, and we've looked at that, we don't just want to stay with forces here, right? We want to move on to that. So since the force applied by a spring varies linearly with the displacement, the work done to stretch or compress the spring is the area under the force displacement graph, right? And that sort of goes back to what you would have done with figuring out work when you did it with graphs in grade 11 and that. You can see it's, just shown right under the graph here in dark. So that means the work since it's the area of a triangle, is just going to be 1/2 whatever the force of the spring is times by delta x. So you get a nice easy equation here. Now I wrote most of this in, but you can actually walk through it a little bit if you want. You can see, okay, well the work is the area under this, which is 1/2 Fs, which is that, times by delta x. And then you can substitute, so this Kx here is just substituting in what the spring force is times delta x. And then you can see that gives you a delta x squared. And here, at the end here, I'm just saying, remember, work is just the change in energy. And since this thing is presumably just starting in its fixed equilibrium position, this is the work you're doing to move it a certain delta x. So that means the change in energy that's gone into the system is assuming you put all of that energy into this. That means this is your elastic potential energy now. So now we have an equation for that, which you'll note looks very similar to another equation for energy. Right? 1/2 K delta x squared. Right? Not that different from 1/2 mv squared, but definitely is different. So we can use this in an example. Excited about elastic potential energy, and I don't know why you wouldn't be excited about this. Student slingshots themselves into the air. Looks like fun too. To do so, they stretch a giant elastic band 3 meters, and we're given the spring constant for that. They're 2 meters above the wall when the band is fully stretched. Then they shoot themselves into the air at an angle of 55 degrees. We want to determine the maximum height above the water. Okay, so we've got a few things going on here. So here we've got this whole slingshot thing here. So they start, let me try to draw this here. They start, let's call this position here 1. Right? So they start right here. And so ordinarily here I would want to define the height of the water as h equals 0. It just sort of feels right? But I just want to look back at the question here because it says we just want to determine their maximum height above the water. That's really it, right? So I don't really need that. So what I'll do is I'll just define h equals 0 here, right? I'll just say let, let me go back to my blue. Right, at this point, right? And so what that means is I've got this distance here, right, above the water, which is 2 meters. And I'll just have to remember that. So when I get my height, I'll just have to add 2 to it, right? But it'll save me a little bit of calculating or whatnot. So let's look at position 2. Let's suppose position 2 is right here. Right when the spring, if you will, or big elastic band or whatever is done catapulting this person into the air. And we're told that they stretch this band 3 meters, right? So that means that this distance here is 3 meters. Since I'm going to have to do calculations with gravitational potential energy, that means this height here, let's say from right, I got to do a little bit of trigonometry here and say, well, if that is 3 meters, right, is the hypotenuse of this triangle, then this height here is 3 sine, it says an angle of 55 degrees. So that means this here is Right. Maybe just move this down a little bit. And I did actually get a number for that already, 2.4575. So that's the actual vertical height that the person goes up while this slingshot is sending them off into the air. Okay, so probably now we can look at, well, and because I'm going to want their maximum height, let's just say, okay, at this point, they're going to have some speed. We'll call this V2 here or whatever. And it's going to send them into the air to some maximum height, which I'll call position 3, and then they continue off into the water. But I only need to know the actual height at position 3, right? So we can use the conservation of energy. So we can look at point 1. It won't do it. E total, which equals, well, I've got 3 types of energy now to consider. I've got the elastic potential energy, I've got gravitational potential energy, and I've got kinetic energy. But at position 1, right when this thing starts, I've defined that height to be 0. So that means there's no gravitational potential energy because H is 0. They're not moving, right? I'm looking at the instant right before this band catapults them into the air. And so the only type of energy they have is elastic potential energy. And we now have an equation for that. That's 1/2 K delta X squared. K I'm given, it's 500, so that's 1/2 times 500. And I'm told that it's 3 meters. And that means I get 2250. Right? And that's why it was helpful, even though I had to figure out the height of the catapult for later. It was good to know that the spring was actually stretched 3 meters, right, in that angle or along that angle. And so now I know the total energy. I know that total energy has to remain constant at every point. So I would like to just ignore point 2, right, and say, okay, the total energy at point 1 is the same as the total energy at point 3. The problem is I need to know the speed at point 3, right? Because this person is, even at point 3, right, they do have a horizontal component to their speed. So I've actually got to do a little bit of dynamics here. I've got to actually figure out at point 2, I need to figure out what is the horizontal component of their velocity. Because when they get to point 3, the vertical component of their velocity, right, will be 0 because they won't be going up or down at all. But they will have an x component to their velocity. And so whatever that x component is at 2, it'll be the same at point 3. And that will be the only speed they have at point 3. But I need to figure out what that is. So I do have to consider point 2. There we go. Again, E total is still exactly the same. So all of that elastic potential energy, right, that we had at point 1 is now going to be gravitational potential energy and kinetic energy. So E at 1 is going to equal EK2 plus EG at 2, which is, I put this in here, that means I've got 2250 equals EK at 2, which is 1/2 mv squared And the mass is 60, right? Plus mgh, so 60 times 9.8 times the height, and that's the thing I already calculated over here. The actual change in height in the vertical direction is 2.4575 meters. And putting in some numbers here, you can see the only thing I don't know here is V2. So I'll save you a bit of work and just say if you plug all that in and solve for V2, you get 5.18 meters per second. Okay. The angle here, though, is going to be the same. Probably not drawn really well, but this is still going to be 55 degrees. And so to get the x component of it, right, I want this part right here. So that's going to be, so I could say that the cosine of 55 degrees equals this x component, which is, right, Vx divided by the V2, which I just figured out is 5.18. Rearrange that. I can do that down here, and I can say that means V2x equals 5.18 cos 55 degrees, which equals 2.9711. And again, I need that because when this person gets all the way to 0.3, they will still have the horizontal component of their velocity, right? That never changes. But that does give me everything I need for 0.3. Right? So once again, the total energy is still going to be 2250. They're not going to have any elastic potential energy anymore, but they are going to have kinetic energy and gravitational potential energy. So 1/2 mv, this is now v3 squared plus mgh, and this will be h3, which means 2250. And V3 is that one we just found, 2.9711 squared plus 60 times 9.8 times H3. And so work out whatever this is, subtract it from both sides, which will reduce the 2250, and then divide both sides by 60 times 9.8. And that will give you H3 equals 3.376. Right. Now, again, remember, this is all relative to the point that I decided was 0, which is technically 2 meters above the water. So I can say, therefore, H max above the water is all there is to it. So last, but certainly not least, this is a big thing in physics, right? There are entire courses where this is basically what you do, right? And so we're kind of just starting it now. We're looking at periodic motion, right? So periodic, right, as it sort of sounds, period, like it comes back at a regular period, is just motion that repeats itself in regular intervals. So if you've studied, sine or cosine functions and what they look like, which you can kind of see down here in this diagram, that's periodic motion, right? It comes back periodically. And also simple harmonic motion, right, is just periodic motion in which the acceleration of the moving object is proportional to the displacement. And that goes back to what we just looked at way over here, where we're saying, look, whatever the displacement is, right, it was a linear relationship. More displacement, more restoring force, right? And it's directly proportional. And so that can give us this phenomenon here, which again is really, really big in physics. We see it all over the place. What we call simple harmonic motion, which usually just kind of abbreviate as SHM. So a mass on a spring is a great example, right? I just went back to there to show you. And you can see that, and you just imagine like what you do is you take this mass on a spring and you displace it a certain amount or compress it a certain amount. How you start really doesn't matter that much. And you let it just oscillate back and forth. If we can ignore friction, right? If we can assume this is on like an air hockey table or, some frictionless surface, then yeah, it's just going to keep oscillating back and forth. I guess we might also be ignoring any energy losses in the spring, like heating and that, but again, reasonable. And then what we're going to get is if we were to graph this thing, right? Let's say we were graphing its displacement relative. So we've got our equilibrium position here right in the middle. We're saying here's where it just sits if nobody touches it. And so in this case, just looking at this graph, this is suggesting it's going in the positive direction first, right? It's getting some amplitude is positive, so it's great. And you could just sort of see whatever the height of this graph is at any point just represents the displacement relative to the equilibrium position, right? So here we've got on the x-axis time, and if we were to draw it, the other axis here, I guess I should actually do it all the way through. Right, this axis here would just be delta x if we're doing this for our mass on a spring, right, and over time. Just as a reminder, I know we looked at period and frequency before. Period is how long it takes per cycle, so number of seconds per cycle, whereas frequency is the reciprocal of that, right? It's how many cycles per second. And I wrote these in here too, just to make sure we took a second to define them. The amplitude, which we've written A, is the maximum displacement. So if you refer to that, it's just what is the absolute farthest position it gets in either direction, right? Maximum stretch, maximum compression. And the period, as I just mentioned, is the time for one oscillation. It's slightly off center here, but do remember for a period, right, it's a full cycle. Sometimes I find if you start, let's say here, and you're looking at a period, some people want to look at this position here and say that's a period, right? But it's not. It's really only done half a cycle, because a full cycle means it goes up to its maximum position, through its equilibrium position, to its maximum compression, and then back, and then the full cycle repeats itself. Okay. For a mass on a spring, I won't go through the derivation or anything like that, but it's actually kind of interesting. If you want to look this up, or I'll put links online. Tough to do sometimes without calculus for these, because they really do set up what we call differential equations. But it does work out. We come to a pretty simple equation here, right? The period is just 2 pi and then the square root of m over v. And that, if you think about it, right, for this type of situation, you think of, okay, 2 pi is basically just a constant, right? And the square root, okay. But what does this really mean? So this says the more massive the object is, right, the longer it's going to take to go back and forth, right? And in this case, that should sort of make sense because, gravity is pulling it down. But if you look at something like, again, this is sideways, right? This is side to side, this thing is happening. And we're ignoring any friction, right? So gravity is just there. It's not really impacting it. So what is actually, making it take more time for the spring to actually pull it back and resist the motion, right? Well, it's the inertia of the object, which is represented by its mass. And in the denominator here, we've got K. And if you think about that, right, the stronger the spring, right, which is represented by the spring constant, right, the more force that's able to apply, because that spring constant is like force per delta x, right? So force per displacement. So the stronger that is, the less the period is going to be, right? It's going to restore it more quickly to its equilibrium position. And if you know those two things, you can figure that out. We can compare that to a pendulum, which you may have looked at in grade 11. Do you remember the period of a pendulum? So it's really similar. 2 pi, and we get this square root. But what makes it go faster? Or what makes it take longer would be L, the length of the pendulum. And on the bottom, we have just G. And this is because it's the gravitational force per kilogram that actually does make it go. So it's an interesting one here where for a pendulum, the mass didn't matter at all. It was actually just G because it's gravity that's making it go back and forth, right? And as we've seen many times with gravity or with objects falling under gravity, right? More massive means it still falls at 9.8, right? Every object, if you can ignore air friction, falls at the same rate. So it really is just G that lands in there. And L is on top because the longer the length is, the more time it'd take to go back and forth. If you wanted to look at the displacement at any time and write this as a sine function, which might be something you might do a bit more in a math class, but we can absolutely do it. This is kind of a simple version of it, but we can just say, well, it's going to be A, whatever the amplitude is, times by the sine of the square root of m over k. In this case, we're using t as our independent variable. So it's a weird way to look at it, maybe. It's x of t, where x is the displacement. So usually you're probably used to seeing that be a y and this be an x, or maybe a theta in a math class or something, which is fine. But for us, it actually works out this way. A little caveat, this is for radians, right? If you're using your angle in radians. If you were doing it in degrees, you'd just have to write it the second way. So that's why I've got two versions of this thing here. And I've got one more example. Okay, so Mr. Brown's car has 4 springs that undergo simple harmonic motion. After hitting a bump, the mass of the car is 800. Oh, yeah, sorry. I just read that in like wrong chunks. So the springs undergo simple harmonic motion after hitting a bump. Often if your shock absorbers are basically shot, and this is what would happen, right? You go over a bump and the car just goes up and down. Up. Okay. So here we're told the car is 800 kilograms. I guess we're ignoring any other mass. After hitting a pothole, the car vibrates through 8 cycles in 6 seconds. We want to calculate the spring constant of each spring. Right, so if we just look at the equations we have, we can say, well, we know that the period t is 2 pi we can look at that, and that's essentially what we want, right? We want the spring constant. We're told 8 cycles in 6 seconds, right? So for that, we can figure out the period. Right, the period is the number of seconds per cycle, right? Or the time, if you will. So that's going to be 6 divided by 8, which I could write as 3/4 or 0.75 if you just want to stick in a decimal, which means 0.75 equals 2 pi times the square root of the mass of this thing is, 800 kilograms. So if I punch this into a calculator, so basically what I would do first here is, okay, let's divide both sides by 2 pi. And then I would write that on the other side. So I've got 0.75 divided by 2. So I could write it that way. Then I can square both sides. Which of course gets rid of that. And that tells me that equals 800 over K. I would just do the reciprocals of both sides. So on the right side, I would make that K over 800. And on the other side, just do the reciprocal of that. That becomes pi over 0.375, which is still squared. And then I would multiply both sides by 800. And that will give me what I want. Okay, so the calculator gives me that. Now, there was a little bit of an issue here though, right? How many springs do I have? Yeah, I got 4 springs, right? So basically, the way I would think of this is, well, they're sharing the load, right? So, and that's not exactly what would be the case with a car, but you could basically assume everything's evenly distributed, right? Each spring would have 200 kilograms over it or whatever. So K for each spring (147.1 divided by 4), which is 14,037, I'll just say. Ta-da.